When it's not used for a long time,
It goes off by itself?
No, no, so when you're done using it for a long time,
Okay.
hold the button. Make sure that whoever uses this doesn't have this on at the same time.
Okay.
So it'll feedback.
Okay. Testing 1, 2. Everybody hear me okay? All right, we're going to get started because it's so easy to get behind. I'm Jim Thorpe. I'm the chairman of the Research and Improvement Committee. I didn't realize I was chairman until last summer meeting, and fortunately I had some good folks to visit with, Leanne Morris, Sarah McKenzie, who couldn't be here, but she's been regular consulting with us, Leanne Morris, and of course Michelle and Taylor. Let's see. We're going to try to archive these sessions. We're going to have, I think Julie Carter is going to make a write-up. We also have 3 interns from New Mexico State who are helping with the AV, and they're also going to write up portions of this meeting. You will find a survey feedback in your packet, and I would ask you to fill it out at the conclusion of each session while it's still fresh in your memory. And we're going to start with the water session, and Tom Patterson helped put that together. I'm asking him to come up and introduce the first speaker.
You know, we had 2.5 inches of rain down in Catron County a weekend before last. Big floods. We've had good rain down there since June 15th. One of our best years for rain. We're going to have one heck of a fire season next spring. We all are, other than maybe folks down in the southeastern part of the state, and little slivers down there. But what we know is that, well, maybe it's just something my dad always harped on. Extremes follow extremes in New Mexico. We have extremely bountiful monsoon rains or rains. We're going to probably be followed up by some pretty horrendous drought conditions. So last summer at the midsummer meeting, we presented to you, to the attendees, Dr. Fred Phillips, who spoke on a study that the state of New Mexico had commissioned. They'd asked 7 scientists here in New Mexico to analyze data and identify what it is that the future looks like in terms of temperature and precipitation. The story's not good. I left that meeting thinking, you know, we need to know more on a specific geographic basis what might be coming down the pike. And so we've asked Dr. Phillips to come speak to us this morning. Dr. Phillips is a retired professor of hydrology at New Mexico Tech. He got his BA in Earth Science from the University of California at Santa Cruz. Got his Master's of Science and his PhD from the University of Arizona. He's been a faculty member at Tech since 1981. His research is focused on groundwater supply, groundwater recharge in deserts, and climatic controls in the hydrology of the western United States. He's been awarded many accolades. The Meinzer Medal from the Hydrology Division of the Geological Society of America, among others. So what we've asked Dr. Phillips to do today is drill down into that, give some background, sure, but drill down to give us, who are located in different parts of New Mexico, more of a geographic perspective on what we might be able to expect. So Dr. Phillips is our first speaker, and he will be followed by Aaron Baylock, who will take the science and give us some recommendations. Dr. Phillips.
Thank you. It's very good to be here and be able to talk to you this morning. The stuff that I am talking about today and the stuff that I talked about in Ruidoso this summer are based on the same material. So I'd kind of like to get a show of hands of how many people heard that talk in Ruidoso. Just, okay, not most of you. Okay, I have some introductory material and then some more specific stuff, so I'll go through the introductory stuff pretty carefully as well, since a lot of you haven't heard that. The material that I'm presenting today was prepared as part of a project that is a collaborative project between the Interstate Stream Commission of the Office of the State Engineer and the New Mexico Bureau of Geology. And basically, the Interstate Stream Commission set the goals and they funded the project, and it was conducted through the Bureau, but using scientists from all around New Mexico, all different institutions. So it was funded as part of the 50-year water plan for the state, which is something relatively new. Previously, water plans were only on a 10-year basis. And the state engineer quite rightly wanted to be able to make longer-term projections and plans and so on that could be useful in a time of changing climate. So if you go to the the Interstate Stream Commission's webpage and you click on the 50-year water plan, you'll come up with this screen. And on the lower left there's a box that says climate and water study. And if you click on that, it will bring up a link where you can download the report. You can also get it from the URL in the upper right, which is at the Bureau of Geology. And this is what the cover of it looks like: climate change in New Mexico over the next 50 years, impacts on water resources. So, what was the motivation for the state engineer to get concerned about this? I think we can pretty well express it in this graph right here. And the main thing that you see, the red on the top, let me see if I can get the pointer working here. I guess it's that one. Yes, well, it's hard to see from that distance. But the red is mean annual temperature since 1930. And we can see that up until about 1975, it was more or less constant. And if you go back in time using either instrumental records or things like tree rings, you get it being pretty constant. And then in about 1975, it takes off. And since then, it has climbed. We have these ups and downs, right, that are the same as over here, more or less. But the dominant thing is this upward trend of about 0.6 of a degree Fahrenheit per decade. And that is very consistent, and it is a very, very strong departure from everything that went before. The mean annual precipitation is in blue on the bottom. And there the picture is not so clear. Starting in about 1975, we have this steady downward trend. And that is an expression of the drought that we all know about and are concerned about right now. I glanced at the Albuquerque Journal before I left my house this morning, and one of the headlines on it was about a meeting of the Colorado River Compact Group trying to work out what they're going to do with historically unprecedented low water levels in the reservoirs on the Colorado. And it's another manifestation of that same trend. But whether this trend of downward precipitation is really part of a long-term situation driven by greenhouse gases in the atmosphere, or whether it is natural variability, is a lot harder to tell than it is for the temperature. So how does our current drought compare in the historical record? And by historical record, I'm looking way back. This is using tree rings and going back to the year 800 AD. And so on the vertical scale, the left-hand side is soil moisture. And I think I was really happy to see this graph, which was in a paper published this year in Nature Climate Change. See it published in terms of soil moisture, because that, I think, is the parameter that is of a great deal of concern to you. More than water levels in reservoirs, how much moisture there is in the soil, right? And so it is a graph of the 22-year running mean of soil moisture. So looking at average soil moisture over 2 decades. And the black, the red on the far right is the instrumental record. The black that forms most of the graph is the tree ring, soil moisture reconstructed from tree rings. And the vertical pink bars are major droughts, mega droughts. And so we can see there's been many mega droughts, but if you take the red line all the way to the right, which is 2022, it's at a lower level than it was in any of those previous mega droughts. So I think you've all probably seen the headlines or the news reports or whatever that we're in the worst drought in 1,200 years, and this is the basis for that. So the drought, of course, is a result of both higher temperatures and less precipitation. And so the same question that I raised on the previous graph applies here. How much of this could we ascribe to increase in temperature, which is due to increased greenhouse gases, and how much of it might be due to natural variability in precipitation? So the authors of this study ran global climate models with and without additional greenhouse gases in the atmosphere. And maybe it's a little hard to see from the back of the room, but there's a blue line right here, and it goes down here. And next to it is a figure 42%. And that is what they came up with as the percent of the soil water deficit that is due to increasing temperature. So in other words, without the increasing temperature, this drought would be no worse than the drought of the 1950s or many other droughts that periods of drought that we see in that part of the graph right there. What about the spatial distribution of this drought? So the map on the left shows the severity of the drought condition by rank. In other words, 1 in this scale on the right would be the worst drought ever experienced in 1,200 years, and 10 would be the 10th worst one. And so those are expressed in these brown colors here. And so for places like in here, that's the worst drought ever. As we go from that really dark color, if we go southeast here, we see that we go progressively lighter in colors until, the southeast part of New Mexico is down in the, it's a bad drought, but it's not a terrible drought sort of condition. It's really, so far as New Mexico goes, it's really focused on the Four Corners area there. And I'm going to show you later on a a blow up of this map here focusing right on New Mexico. So be alert for that to come up in a moment. So they did the same part of the study that I described before. They ran the model without increasing temperature from increasing greenhouse gases, and this is what you get instead. And you see that the southeast part of the state would not be experiencing any long-term drought at all. There would be kind of a moderate level of drought right up in the Four Corners, but it would be nothing like what we're seeing now without the higher temperatures that I showed you in a couple of graphs ago. So, what can we project for the future? This figure here shows the temperature since 1900. This is temperature change in degrees Fahrenheit. And this kind of a gold-colored line here is essentially the same as the temperature plot in the first figure that I showed you. And again, of course, since it's the same data, it shows the same pattern, more or less constant fluctuations around a constant mean up until about 1975, and then starting to go up. So what can we expect for the future? That depends. There are uncertainties in the projections that come from all of the various factors that go into trying to model and understand this, but by far the biggest source of uncertainty is how much greenhouse gases we're going to have in the atmosphere in 2100 over here on the right-hand side of the graph. So if we go on with business as usual, more or less the same rate of emissions we have now, we're going to end up here, which is an increase of between 10 and 14 degrees Fahrenheit over the 20th century. And that is really an awful number. You know, think of the situation we have today, but with 10 degrees higher average temperatures. It would be extremely bad. If we manage, you know, they had that meeting in Egypt last month and tried to settle out reducing emissions and so on, and apparently with some success. If those sorts of things are successful, we substantially reduce emissions of carbon dioxide and other gases. We're going to end up being on the order of 4 to 6 degrees warmer, which is survivable at any rate. These models are scientifically considered to be pretty reliable, right? As I say, the main uncertainty is the amount of greenhouse gases in the atmosphere. So there's a fair degree of confidence that we are going to see increasing temperatures for at least the next 50 years. This is more specifically for New Mexico here. And so it's more, I'm not going to spend much time on it, it's more or less the same as the previous one, but you know, shows you in more detail. Here's 2020 and 2070, and in this case it's 6 degrees higher. What was I going to say about that? Yeah, I don't think I need to say more there. So, what about the spatial pattern? I've been asked in this talk to focus on the sort of regional impacts of future projections for New Mexico. And so this is part of that. What we see, very interestingly, is that the rate of increase of temperature is not uniform across the state. And so we see that the highest, and I'm having a little trouble from my oblique angle reading the scale up here, but you know, the highest values of change in temperature are right up at the Four Corners, and the lowest values are down here in the Boot Heel and over in the southeast part of the state. Now, this doesn't mean that these parts of the state aren't going to warm. What it really means is that they're warming more slowly than the Four Corners area. However, so this gives us some clues as to what you all might expect in different parts of the state. And it's not good news for those of you who live up in the northwest corner. However, when I looked at this and then I looked at that paper that I showed you earlier with the tree ring stuff in it, I almost fell out of my chair, because this is that figure that I promised you there, with the severity of drought being greatest where the colors are dark and least where they're light. And if you compare those two figures, they are, for all practical purposes, identical. And I don't think anybody has ever pointed this out before. I mean, this is a pretty new result right here. But it's not a good news sort of thing, because what it says is that the pattern of drought is following the pattern expected for temperature increase here, and that as temperature continues to increase, it is likely that we're going to have this thing spreading essentially over more and more of the state to the southeast. So it does establish a strong linkage between the temperature increases and drought. Okay, so obviously as a result of increasing temperature, the state is going to become more arid. And there is a quantity which is called the aridity index, and that is the ratio of potential evapotranspiration to precipitation. That is a standard expression in hydrology for how arid a particular region is. So if you have this, potential evapotranspiration equal to precipitation, then you have an aridity index of 1. And there's lots of areas of the world that have aridity indexes between 1 and 0. Those are humid areas. And then in desert areas, it goes to values of 10 or 15. In other words, that you're capable of evaporating 10 or 15 times the amount of precipitation that actually falls. So on this map of New Mexico, the more humid parts that are below 1 are in either, kind of whitish or blue colors. And the parts that are the more arid parts of the state are in, so these are down around or up around 10 for the aridity index, places like around Las Cruces or right up in the northwest corner there. And so, we all know how vegetation and everything like that varies depending on this aridity index. You can pretty well predict what you're going to see in different parts of the state based on it. So what do the projections say about aridity in the future? So the graph, the map on the right is the increase in the aridity index to 2055, so not that terribly far in the future. And the darkest colors down here, and it's in terms of percent of the current aridity index. So the darkest colors are about 40%, and the lightest ones are between 5 and 10% here. And immediately you can pick out, right, there's a correlation between the two graphs. And the correlation is that the areas that are the most blue on this graph are the most brown in this graph. So that says that the areas that are currently the most humid are the ones that are going to dry out the most. And again, if you want to try and get some feel for what's going to happen in the part of the state that you live in, if you're down here around Las Cruces or south of Hobbs, it's going to be drier, but it's not going to, in a relative sense, not going to be that huge. But if you're, someplace really nice, like up in Shama or something like that, it's going to become, relatively speaking, a lot drier. Okay, so we've been talking about temperature mainly so far, but we also need to consider precipitation. And it's hard to say anything very definitive about precipitation, and I want to be really clear that this is a limitation of the projections that I'm showing you here. And basically it comes from the fact that the models that are used to produce the numbers that go into this analysis are global models. And so they are mainly oriented trying to understand these processes on a global scale and get a handle on that. And they're not optimized for particular areas of the globe. And so in terms of precipitation, the results they output, in terms of temperature, the results they output are quite consistent. But in terms of precipitation, they're kind of all over the map. And so some of the models will show increasing precipitation for New Mexico, others will show decreasing, some will show not much change. So this graph makes it look like there's probably not going to be much change. Really, what the graph is saying is there's a lot of uncertainty about the precipitation, and so we have this real wide bound here, right? Compare that with the narrow bound on that temperature graph I showed you a few slides ago. So it's not really saying that there's not going to be a change in precipitation. It's just saying that we don't currently have a good enough handle on it to understand it. And I'll just mention at this point, I'm a co-principal investigator on a proposal to the National Science Foundation, which has a couple of objectives. One of those is to try and find a way to select the global climate model outputs that are most accurate for New Mexico and use those for future projections. And that would cut down a great deal on this uncertainty here. Another one is to try and come up with climate forecasts that are on a shorter time frame. So maybe we could have reasonably reliable 5 or 10 year forecasts instead of things like 50 years, which is more of what we're emphasizing here. So that's trying to get products that would be more useful for you all. Knowing what's going to happen in 50 years gives you the general trend, but none of us are worrying about that on a day-to-day basis. But 5 years, yeah, maybe. Okay, so the conveners asked me to emphasize the sort of regional things. So the graphs that I am putting up here are seasonal distributions of precipitation. And again, the precipitation is not very confident in the outputs, and seasonal distributions are less. So I would certainly take this with a grain of salt. It's the best that we have now. It's at best moderately useful for you all. But let's go through and see what it says. So the scale, unfortunately, is kind of small, is up here, but it's pretty intuitive. Increases in precipitation are in green, and decreases in precipitation are in brown here. And so it starts out with winter here, and winter is basically, let's see, am I right on that? Sorry, let me go check. I'm having a hard time reading it. So yeah, I'm at a real sharp angle to the screen, so I want to make sure I'm pointing at the right thing. So this is winter here, and it shows precipitation being probably somewhat less, but not hugely so, and especially down in the southwest part of the state. Then if we move to spring, this is where the news is really pretty bad. To my mind, it's the worst. And basically, it shows the entire state having fairly significant decreases in spring precipitation. And in terms of rangeland conditions and so on, spring precipitation is really critical. And so also in terms of our fire situation, it's critical. And so, you know, if this is really accurate, which we can't be sure at this point, that's definitely not good news. The summer story is very interesting. This is the one place that we have the best agreement between all the models, which is sort of surprising because summer precipitation is harder than winter to predict. But what they show is a drying in the northeast quadrant of the state and perhaps increases in summer precipitation in the southwest part. So that's one place where there's a strong regional pattern. And then finally in autumn, again, a little drier for the most part, but not, it's sort of like the winter, right? Not a real strong pattern anywhere. Okay, so what can we anticipate as the effects of these pretty confidently predicted changes in temperature and less confidently predicted ones in precipitation? Well, part of it, you know, we all know this is historical data, not projections, but it is area burned, square miles burned in fires that are greater than 80 square miles. And we see that through most of the 20th century, there was almost nothing. And then starting right about 2000, we ramp up. We have the two largest fires in the history of the state, both this year. And that pattern is almost certain to continue and to increase. Part of it, obviously, is due to excessive fire suppression in the 20th century, but the increasing temperatures are very much playing a role. And we see the effect of those increasing temperatures in things like the Black Fire here this spring, in the Black Range, in which, you know, the rate of spread of the fire was unprecedented, and you can see the truly frightening amount of energy being released as that fire started up. And the result of that has been that forests that we thought were only and most moderately affected by fire are now very vulnerable. So this is pinon juniper vegetation in the Jemez Mountains after the Las Conchas fire in 2011, and it's essentially a moonscape. And this is pretty unprecedented. What that fire is resulting in is long-term vegetation change. So in the Las Conchas fire was now 11 years ago. For most of the area of that fire, the ponderosa has not been replaced by new ponderosa, regrowing ponderosa, or other normal succession. Instead, it is scrub, in this case oak scrub vegetation, which seems to be relatively permanent. Time will tell, but that's what it looks like. And of course, if you're talking about grazing, there is a huge difference between open ponderosa forest and dense scrub. The scrub is not capable of holding the soil onto the landscape where the landscape is steeper, and so here you see the scrub and the soil under it being ripped off on these steep slopes in Santa Clara Canyon, and probably by the end of the century or even sooner, this is essentially going to be a bare rock landscape. And what happens to all of that soil and boulders and so on that are stripped off of the hill slopes? They end up on the riparian areas down below and do more destruction down there. And even without fire, we are losing soils. And just because of drought and vegetation loss, this, I believe, is in the northwest part of the state. And this, over here, you see, vegetation, brush and grass and so on. And then here is just bare rock. And this was all under soil and vegetation 20 years ago or so, and it's being progressively stripped off here. So, as temperatures increase, we're going to see more and more of this. Okay, so a summary. The impact of climate change on New Mexico is unfortunately overwhelmingly negative. Temperatures are almost certainly going to continue to rise. Aridity will increase due to higher air temperatures, and there will be less runoff and less recharge. Snowmelt earlier and less, and decreased surface water, greater use of groundwater. So I'm going to go on and finish up by focusing in on different regions of the state. We divided up the state into the high mountain areas, the northwest high desert, the Rio Grande Valley, and the southwest basins, and the eastern plains. So in the high mountains, these are going to be the places that are most impacted by climate change, and the impacts will be felt throughout the state because of decreased water supply. The increased wildfire and permanent vegetation change will also, the debris and so on will move downstream. In many areas, forests will be lost to fire or directly to drought and will be replaced by scrub. Pinon juniper will move up and may expand, and grass will probably be reduced. The vegetation conversion will lead to increased soil erosion. Ponderosa slopes may eventually be converted to bare rock if they're steep, and debris washed from the slopes will cover the valleys. The northwest high desert is going to see the most rapid increase in temperature, which will lead to the strongest droughts being focused there. There may be an increase in the intensity of summer thunderstorms. I think loss of soil, increased dust, increased arroyo incision, and possible transition from grasses to shrubs. The Rio Grande Valley is mainly going to be affected by the irrigation water supply and the water supply for other things as well. But the southwest basins are going to feel the smallest impact of changing climate. There may be reduced grass due to increased summer drought, although remember that graph showed a possibility of increased summer precipitation. This year would certainly, it's anecdotal, but that may support that, right? The desert vegetation is not going to change much. Creosote bush is one of the hardiest things in the world, right? And so it's not going to feel the increase in temperature. More intense summer thunderstorms and possible increase in monsoon rains. And finally, the eastern plains. There, for what it's worth, the models indicate a decrease in summer rains, but likely increase in extreme precipitation. When it does happen, it's likely to be more intense. There's going to be a greater average increase in aridity than the rest of the state except for the high mountains. If the projections are correct that there's going to be a decrease in summer rain, then that would result in a reduction in grazing. Loss of soil, increased desertification, and increased dustiness. So the summary, we will be among the states hit worst by changing climate. Change in precipitation is uncertain, but temperature increase is pretty darn certain, and it's going to drive up aridity all by itself. The higher mountains are going to get the strongest impact, resulting in forest conversion. The northwest highlands and eastern plains will see continuing increasing drought. Not all the time, but the pattern will. So I'm sorry, I was shifting around. What was the question?
What happens more or less in 1975 going forward?
So you're asking why does everything start ramping up in 1975?
Yes.
Because that is the point at which the influence of increasing greenhouse gases in the atmosphere became larger than natural variability. So if you could have some super accurate model that, could track what temperature you would have with increasing greenhouse gases and without, you would see that before that it was, kind of, a little bit above the actual line. But if you look at the graphs of greenhouse gas concentration in the atmosphere, you see that that is really when they start to increase past the critical point. So it's very closely connected to the carbon dioxide and other gases in the atmosphere. Other questions?
You discussed the tree ring data, which goes back to 800 AD.
Right.
And maybe I'm wrong on this. There's not any way of calculating or estimating temperature that far back. Is that correct?
No. I mean, there's many ways of estimating temperature that far back.
The actual 1900 forward is actual measurements.
Right.
Before that, it would be conjecture.
Well, I mean, it's what we call proxy measurements, right? And so there's many different things that depend on temperature. A lot of the methods that we use to reconstruct that use isotopes, and the, abundance of the isotopes in certain minerals and so on depends on the temperature at which they precipitate. Same thing with ice. So you can go to the poles and look at the ice. And so there's a large number. I mean, there's probably 20 different proxies for temperature that paleoclimatologists use, and they're all in reasonable agreement,
What I'm getting at is that the tree ring data shows decreases in precipitation and then subsequent increases back to normal or whatever.
Right.
Temperatures would likely follow somewhat that pattern, right?
I agree, but I would emphasize the somewhat. The fluctuations in temperature are much smaller than the fluctuations in the drought index, right? So yes, and the drier periods are hotter. We always see that. But the magnitude of the temperature fluctuation is small. Those were mainly driven by changes in precipitation, not changes in temperature, unlike the last 20 years.
Dr. Phillips, thank you so very much.
You are welcome.
We appreciate that.